Hi, in this video I'll be introducing polar diagrams in context of lighting theory. So in previous questions we introduced the basic idea of lighting theory and the relationship between the luminous intensity from a source, the luminous flux, and the illuminance on a surface that's perpendicular or inclined relative to the source and the distance between the source and the surface. And we were able to calculate the illuminance using either this equation for perpendicular planes or where a plane was no longer perpendicular, this equation here. Now, in all of these questions that we've done beforehand, we were provided with the information about the light source in terms of its luminous intensity, its candelas. So in this one, for example, it was 1,000, and this one it was 2,000. But you may not always be provided with this information. You'll be provided with the information about the lamp or the luminaire specifically. Use this then to extract the luminous intensity, the polar diagram. So let's see the screen. I'm putting up an example of a polar diagram on the screen right now. So this is a polar diagram for a given lamp. And how we read this is this pattern we can see on our polar diagram is a characteristic curve for a given light. And we use this characteristic curve to work out the number of, or the size of the luminous intensity for a given lamp based on the position underneath. So, for example, if we are standing directly underneath this lamp, that would be 0 degrees off center. We come straight up as if we're drawing straight into the middle of this polar diagram until we hit the characteristic curve. Then, using these dotted lines, each one represents a number of candela per thousand lumens. So for example, this outer ring is 1,000, this inner one is 800, 600, 400, 200, and then 0. So if we come up from 0 degrees and hit here, that's somewhere between, by the looks of it, 800 and 600. So we can say maybe 750 candela per 1,000 lumens of the lamp. Now take, for example, if we are 45 degrees away from the lamp. In this case, we come up and we hit the characteristic curve. And in that case, we're only about between 600 and 400. So I would say that's approximately 500 candela per 1,000 lumens. So for a given lamp, you can work out the amount of lumens it produces, and then using its characteristic polar diagram, we can work out the luminous intensity. So let's do an example of one of those on a piece of paper. This again is polar diagrams. Now let's assume we have a source, but we don't know what the luminous intensity is yet, so we'll leave that. And we'll first consider just the case of directly beneath it, or perpendicular. Now from the given that I was just looking at, we worked out that at 0 degrees, which is directly underneath the source, it was approximately 750 candela per 1,000 lumens. So how do we use that information then to get the luminous intensity? The first thing we also need to know about this source of light is that its output is 1500 lumens. This is provided from the manufacturer of the light. But with that then, if it's 1500 lumens and we get 750 data per 1000 lumens, then the luminous intensity for this example will be 750 over 1000. That's from our polar diagram, multiplied by the 1500 lumens of our lamp. And you can see that this is lumens, and lumens will cancel. And we end up getting luminous intensity of 1125 candela. So then we'll call it point A. At point A, or at 0 degrees then, our luminance is just as it's going to be 125, and I forgot to mention this, the distance between it is 2 meters, so that's 2 squared. We end up getting 281.25 lux. And once we have this, because we now know that it's 1125, work out then for, let's say, this angle here, theta, is 45 degrees. Lines here just to separate the answers for these two parts. At 45 degrees, if I go back to the polar diagram, my polar diagram, 45, it's approximately, I would have said 500, but maybe a little less, about 450. So come around here, somewhere between there, it's about 450. So with that information, we can go back and we can say, right, well, that's 450 data per 1000 lumens. The output of the light in terms of lumens doesn't change at this stage, so we have a new intensity because we're at a slightly different position to where we were originally. So now this becomes 450 over 1000 multiplied by 1500. And that comes 675 candela. And we have to use the version of this that is for non-perpendicular arriving light. So it becomes I times the cosine of theta squared. So now using a slight bit of trigonometry, we can work out then that that's 675 multiplied by 0.707. That will be the cosine of 45 degrees. And that new distance here is about 2.828 squared. That works out at 60 lux. So you can see the difference there. We count now that we're no longer directly underneath the source. So as a result, our luminous intensity has also changed. You can see a reduction in the luminous intensity, but also we're further away from the source. And our light is falling on a larger distance because it's no longer perpendicular to the plane that we're falling. So this is one example of how to use a polar diagram. If we go back to the screen, we can pull up an example of this in Dialux, where I've got one light fitting in a room, and I've calculated the lux plane, which is approximately 2.3 meters from the light source. So we can see here that this one is an average directly underneath the light of about 400 lux. And then as we step out, it starts decreasing. So 300, 250, 125. So we can see that's not a linear relation. What's also interesting about using Dialux for this is that we can pull up manufacturer specific data sheets on the different light fittings. So on the screen at the moment, I've got a product data sheet provided that shows the polar diagram for this light fitting, the one I just showed you in Dialux. Along the side here, we have the lumen output of the lamp. And we've also got the lumen efficacy. So we could, if we had the electrical power of the lamp, we could use that to get the lumen output either. But the important thing here is on the apologies, I meant to zoom in on that. We on the right here onto the polar diagram gives us the angle underneath our fitting and the unit here of each of those circles, candela per 1000 lumens, just as we had another one from question. And then in the polar diagram underneath, each of those rings represents a number of candela per 1000. So for example, on this light fitting, directly under degrees, we would have approximately 480, maybe 490 candela per 1000 lumens. And then we can use that information along with our lumen output to work out the luminous intensity. And compare that then to the calculations in Dialux. So just to refresh, in this example, we just did it. We did not know our luminous intensity, information from our polar diagram, and we were able to use that to work out the intensity per lumens, combine that with the lumen information of the light to get the overall intensity for that position, and this then allows us luminance. And the same then for the second position here at 45 degrees.